Hello, everybody. Today we have a great event. Today, Professor Edward Witten give a talk for us. The title of the talk is Gravity and Cross Product. Okay, please, 1 hour. And Professor Witten said that if somebody want to ask question, you can do this during the talk. Okay, please.
Okay, well, thank you so much for the invitation. And I'm glad to have the chance to give this talk. So my starting point was actually the work by Lodheiser and Liu in the two papers I've mentioned here. They studied N equals 4 superangle-Mills theory in a novel point of view. And as I'll explain, they identified an emergent von Neumann algebra of type 3-1 in the large N limit. This is above the Hawking-Page or Hagedorn transition. So I'm going to begin by explaining how they did that and how they made some interesting proposals on probing behind the black hole horizon. Then I'll calculate some corrections of order 1 over n squared, or equivalently from a bulk point of view, corrections of order Newton's constant g to their picture. And we'll find that these corrections qualitatively change the algebra, which will become a von Neumann algebra of type 2 infinity. What's interesting about that is that entropy, for example, is well defined for type 2 infinity, but not for type 3. So the 1 over n squared corrections will put us in a situation where entropy, or at least entropy differences, are well defined. The reason it's possible for a perturbative correction to change the nature of the algebra is that in the leading large N approximation, the algebra contains a central generator, which is related to the black hole mass, or equivalently the horizon area. Having a large center makes the algebra potentially unstable to perturbative corrections. And we're going to find a perturbative correction that deforms the algebra to something more stable, which will be a type 2 infinity algebra with a trivial center. Since I'm only analyzing one particular correction of order 1 over n squared, you can ask if further perturbative corrections lead to further changes in the nature of the algebra. Though I don't have a rigorous proof, I expect the answer is no. I expect that once the center is eliminated, the algebraic structure is stable against further perturbative corrections. It's not non-perturbatively stable, because if n is an integer, no matter how big, the algebra of observables outside the black hole horizon is actually of type 1. So perturbation theory will give us only halfway. Okay, I think I explained it on this page. The deformation from type 3-1 to type 2 infinity brings black hole physics closer to ordinary quantum mechanics. A type 3 algebra doesn't have many of the things we're used to, such as pure states, density matrices, and entropies. So the fact that the operator algebra at n equals infinity is of type 3 is one aspect of the black hole information problem. A type 2 infinity algebra still doesn't have pure states, but it does have density matrices and entropies. Well, it almost has entropies. As I'll explain, it has entropies that are defined up to an additive constant, similarly to entropy in classical physics. So in classical physics, the first law, by macroscopic arguments, classical physicists discovered there is a state function S. Oh, sorry. Didn't mean to do that. There is a state function S that is defined by this relation dE equals TdS minus PdV, except that only defines it up to an additive constant. So the additive constant was defined quantum mechanically, but classically, it's really an ill-defined constant. And so what we're going to find is that with the 1 over n corrections included, black hole entropy is similar to entropy in classical physics. So to really solve the black hole information problem, we should get a type 1 algebra, the algebra of all operators on the Hilbert space, which would be the space of black hole microstates. So what's going to happen to us today is that, at least from this algebraic point of view, we'll kind of get halfway. We'll get from type 3 to type 2, but not to type 1, which we expect would happen at any given finite n, but not in perturbation theory in 1 over n. So I'll begin by reviewing the work of Lodheiser and Liu. So with a suitable normalization of the fields, the action of n equals 4 super Yang-Mills has a single overall factor of n in front and no n's inside the trace. With that normalization, the expectation value of any single trace operator, so let W be any polynomial in the fields and their derivatives with no explicit n's. Then the expectation value of trace n is of order n, and its connected two-point function is of order 1. And more generally, the connected k-point function goes like n to the 2 minus k. Now, because the expectation values diverge for large n, to get an algebra with a large n limit, we subtract the expectation values, which means we subtract the thermal expectations if we're working at positive temperature. So we consider operators such as trace W minus its expectation value, which I'll call curly W, and the algebra they generate. Well, LL make this construction for a thermofield double state at a temperature above the Hawking page temperature. So they consider a left and right copy of the n equals 4 super Yang-Mills theory, describing the left and right sides of the black hole. So the picture is roughly like this, where, well, the gray region is to the future or past of the horizon. The two white regions are on the left or right of the black hole horizon. And in this picture, I've also drawn an initial value surface S. So as I've explained, subtracted single trace operators have Gaussian correlation functions of order 1. Higher order correlators vanish. So it follows that their commutators or anti-commutators are C numbers. Well, the matrix of commutators has a kernel, which will be important in this lecture, and we'll discuss it in a moment. If we ignore the kernel, which corresponds to the center of the algebra, by definition, the kernel of the commutator of matrices, the kernel of the matrix of commutators consists of all linear combinations of operators that don't have any commutators. In other words, they're in the center. So the kernel corresponds to the center. But if we ignore the kernel, then since the commutators are C numbers, the algebra generated by the operators such as W is a generalized free field theory. We get two generalized free field theories, which I'll call A left 0 and A right 0, to the left and right of the black hole, respectively. The subscript 0 means that we're not yet including the kernel. So we'll remove the subscript when we do include the kernel. The duality tells us that AL0 and AR0 are the same as corresponding bulk algebras with the little l or little r of operators to the left or right of the horizon. So AL0 and AR0 are algebras of type 3-1 because AL0, for example, or AR0, say, is, you could think of it as the algebra of all operators on half of the initial value surface. So if you take the half of the initial value surface, that's over here on the right side, operators on half of the initial value surface are the same as operators in the white region. And gauge gravity duality tells us that that's the same as the algebra on the right boundary. But because we only take part of the initial value surface, we get an algebra of type 3-1. This bad von Neumann algebra that doesn't have irreducible representations or any nice things. And that's the statement that the operators outside the black hole horizon are a type 3 algebra. So from the bulk point of view, what the 0 means in AL0 and AR0 is that these algebras are obtained by quantizing bulk fields in the presence of the black hole of specified mass. We don't yet consider fluctuations in the mass. So again, we'll remove the subscript when we incorporate fluctuations in the mass. Well, the kernel of the commutator matrix is related to the conserved charges of the black hole. The conserved charge that's important in the sense that including it changes the nature of the algebra is the black hole energy. So to keep today's lecture simple, that's the only conserved charge I'll discuss today. In my paper in the last few pages, you can read an explanation of what to say about the other conserved charges. but it doesn't lead to any surprising conclusion. Since the black hole mass area is not a generator of L0 or AR0, the Hamiltonians HL and HR that generate time translations on the left and right boundaries must not be part of the boundary algebras AL0 and AR0. The way that happens is straightforward. The definition of, for example, HR has an explicit factor of n. Something like that is the standard formula for HR. Above the Hawking page transition, because of the explicit factor of n, HR has an expectation value of order n squared, and in particular doesn't have a large n limit. Of course, we could subtract the expectation value and look at a subtracted operator, HR prime, HR minus its VEV. It still doesn't have a large n limit because its mean squared fluctuation is of order n squared. If we divide HR prime by n, we get an operator that does have a large n limit. I'll call it U.
Hi, Edward. Can I ask a small question?
Yes.
Yeah. So, I mean, here, what do you mean left and right side of the horizon?
I'm assuming you're familiar with the two-sided black hole solution of general relativity. And then in the two-sided black hole, where did I draw it? The two-sided black hole, literally, there's a left and a right side. There are two asymptotic infinities. I call one the right and one the left. I think the terminology is standard, actually.
Okay, but normally we take only one side, and the other side is some other universe or not physical.
It's up to you. It's up to you, but I would say I don't agree with you. Many authors discuss both. We could decide we're ultimately only interested in observations on the right side. And in a sense, that's what we'll ultimately do. But the picture is clearer if you have both of them in mind.
Okay.
If we simply divide HR prime by n, we got the operator that I'm calling U, which does have a large n limit. But now you'll see that because we divided by n, U is central at n equals infinity. In other words, what's the commutator of U with some operator V? Well, it's 1 over n times the commutator of HR. HR generates time translation, so the commutator of HR with V is minus I dV dt, but now we've divided by n. So you can see that the right-hand side vanishes at n equals infinity, and therefore U is central in the large n limit. So HR generates time translations, but it's not present in the large n algebra. That means that time translations are a group of outer automorphisms of the large n algebra. That was very important for Leutheiser and Liu. So let B be a time band on the right boundary, where the times are either finite times or possibly plus or minus infinity. So B is the band in which time is bounded below by T0 and bounded above by T1 for some T0 and T1. And let AR0 with the superscript B be the algebra generated by the single trace operators in B. If time translations were in AR0, we could use time translations to conjugate any operator into the time band, and so AR0B would be the same as AR0. But in fact, HR is not in the large n algebra, and therefore it's possible for AR0B to be a proper subalgebra. And it's not just possible, but it's true. And this still makes sense to all orders, finite orders in 1 over n, because if an operator is in the time band, its time derivatives of finite order are in the same time band, are still local operators in the same time band. To get out of the time band, you have to exponentiate the action of HR. And that would be non-perturbative in 1 over n. But perturbatively in 1 over n, you can't move an operator out of a given time band. So the work of Leutheiser and Liu in part involves studying the algebras for time bands in a way that I'll explain in a moment. Now let H sub TFD be the thermofield double Hilbert space in the large n limit. So it's the Hilbert space. So in the bulk, it's the Hilbert space we get by quantizing small fluctuations about the eternal black hole. So in particular, it's well defined. It contains a vector psi TFD that corresponds to the Hartle-Hawking state. That's the state that purifies a thermal ensemble on the right-hand side. From the boundary point of view, HTFD consists of all the states you can make by acting on psi TFD with the operators of the generalized free field algebras AL0 and AR0. It turns out it's enough to use one of them. So you could use just AL0. AR0 doesn't give additional states. So all this is at a fixed temperature, so it doesn't include fluctuations in the mass or energy of the black hole. Although HR and HL do not make sense as operators on the thermal field double Hilbert space, the difference does. It annihilates the thermal field double state. It annihilates the Hartle-Hawking state. And it has a finite action made on any state made by acting on psi TFD with a few field operators. So therefore, it has a finite action on a dense set of states in the thermal field double Hilbert space, and therefore it's a well-defined operator. Another explanation from a bulk point of view is that H hat is a well-defined operator because it corresponds to a killing vector field V of the eternal black hole background. Now here's a question. How would you understand in bulk the fact that H hat is well-defined and HR and HL are not? So here I've drawn again the picture of the two-sided black hole. As I said a moment ago, the bulk dual of H hat can be defined as an integral over a Cauchy hypersurface S. So now I'm going to make use of this hypersurface I've been drawing, and I've chosen the hypersurface to pass through the bifurcate horizon, the point where the past and future horizons meet. And then I've labeled the parts of it to the left or right of the horizon as SL and SR. Well, if, as in the picture, we choose S to pass through the bifurcate horizon and split it geometrically as the union of left and right piece, you can try to define HR and HL as integrals over the left and right portions. And I've included a minus sign for HL because since the vector field V is future going time-like on the right side, it's past going time-like on the left side. So the minus sign is included so that formally both H and R and HL propagate toward the future in time. So formally, we can define HR and HL, little hr and little hl this way, and then H hat with the little hr minus little hl. The trouble with this definition is that because of fluctuations near the horizon, the quantities HR and HL do not make sense as operators. So remember, capital HR and capital HL did not make sense as operators because they had fluctuations of order n squared. The same thing happens to little hr and little hl, except we would interpret the large fluctuations as divergent fluctuations near the black hole horizon. So if you calculate, you'll find that little hr on the thermal field double state, its norm squared is infinity. So little hr on the thermal field double state is not a Hilbert space state. And the same is true for any other state in the thermal field double Hilbert space. Once it's true for psi TFD, it's true for any other state, because any other state basically is made by acting with psi TFD on finitely many field operators. And that doesn't affect this infinity. I'd like to mention that although little hr and little hl don't make sense as operators, they do make sense as quadratic forms. That means for suitable states, you can define the matrix elements of HR and HL between those states. The same is true for capital HR and capital HL. They didn't make sense as operators because of fluctuations, but they did have well-defined matrix elements between suitable states after subtracting the thermal average. So to summarize part of this, from a boundary point of view, capital H hat equals HR minus HL has a large n limit, but the two operators do not separately. From a bulk point of view, little h hat is well defined, but cannot be split as little hr minus little hl. And part of ADS-CFT duality is the fact that little h hat is beta times big H hat, which connects these statements. The factor of beta is there because the vector field V, well, I didn't really tell you how to normalize V, but if V is normalized as the Lorentz boost at the horizon, then it's beta times a time translation generator at infinity, and that gives this factor of beta. Now, I want to explain one more aspect of the work of Liu and Leutheisser, and then I'll go on to explain what I did with 1 over n corrections. The modular, I won't quite completely explain this. Well, okay. I might assume slightly more familiarity with some fancy words. I may not be able to explain some background in as much detail as I will in the rest of the talk. What's called the modular operator of the state psi TFT for the right algebra is e to the minus beta h hat, which I'll call delta. So what's called modular flow by delta to the minus it over beta is the flow by e to the it h hat, which is e to the it times hr minus hl. So that's time translations by time t on the right boundary and by time minus t on the left boundary. So that means that on the right algebra, modular flow just generates time translations. Now let B be the time band from t0 to infinity. So I've drawn it here. Here's the thermofield double again. Now I've drawn, sorry for the phone ringing here. I'm afraid I can't do anything about that. I've drawn the time band on the right boundary. It goes from t0 to infinity. And then in black, I've drawn what's called the causal wedge of that time band. That's all points with the property that you can reach them from B and then also receive a signal that comes back. So they're the points that can be both influenced and seen from B. So if an observer in B wants to do an experiment to know what is out here, rather than just passively observing it, you shine a laser beam and see what comes back. That only works for the points in the black region, which is called the causal wedge. So modular flow of the right algebra generates time translations. And if the flow parameter is positive, it moves this band B into a smaller band of the same kind. So it generates, it conjugates the algebra of the band into itself, as explained here. And that's a very special situation, which is called a half-sided modular inclusion. And it has very strong properties, which Liu and Leutheisser used to suggest a way to probe behind the black hole horizon. Although I think you can't read the end of that sentence. So perhaps that was their most interesting idea of using this to probe behind the black hole horizon. Well, it's one of their most interesting ideas anyway. But I want to explain it in detail because, again, I'm going to go in another direction and discuss some 1 over n corrections. So now what we're going to do in the rest of the talk is to include the central generator U and discuss some 1 over n corrections. Well, the thermofield double state, one way to explain what's the thermofield double state for the algebra AR0, it's defined to reproduce thermal excitation values for any operator in AR0. So the thermal excitation value, which is what this is meant to be, by definition of the thermofield double state, it's the excitation value of the operator A in the state psi TFT. In other words, psi TFT is what's called a purification of the thermal density matrix. So the excitation value of A with the thermal density matrix is the same as its excitation value in a pure state that purifies the thermal density matrix. And that pure state is psi TFT, the thermofield double state. Except, well, this defines the thermofield double state for all the operators except the central operator. But we can extend the definition of the thermofield double state in both the algebra and the Hilbert space and the thermofield double state. So for the algebra, we just define a commutative algebra A sub u of functions of u. If we want to include u in the algebra, obviously it needs to be able to act on something. but it's central, so nothing in the algebra doesn't commute with it. We just add a new Hilbert space. Well, in the algebra, we just say we have the old algebra tensored with functions of U. AU is the algebra of functions of U. Now, if you want the extended algebra to act on something, what it acts on is the old Hilbert space tensored with L2 of R, where L2 of R is the space of square integral functions of U, with U acting by multiplication. So now we've extended the algebra, and we've extended the Hilbert space so that the extended algebra can act on the extended Hilbert space. So what's a typical element of the extended algebra? Well, there are different ways to write it, but see, an element is a function of the old algebra, A, times a function of U, but sort of a basis, by Fourier transforming a basis for all functions of U, or the Fourier exponentials, e to the I little u times big U, where U is a real number. And if we take a linear combination of such things in general and integral of them, we get the most general element of the extended algebra. So this is a typical element of the extended algebra, except that you shouldn't assume the function little a of U is smooth. For example, little a of U might contain a delta function of U. So we can also define an extended thermophile double state that captures thermal expectation values of operators in the extended algebra. We just note that in the large N limit, U has Gaussian correlation functions. All the single trace operators have Gaussian correlation functions of the large N limit. U does too. Its 2-point function is proportional to the heat capacity, dH d beta, the heat capacity of the black hole, or the thermal ensemble. So anyway, U has Gaussian correlation function, so there's a Gaussian function G of U, so that the excitation value of U to the K for every K is the integral of U to the K times G of U. So for the extended thermophile double state, we can just take the old thermophile double state tensored with G to the 1/2 of U, and that gives an extended thermophile double state that I'm calling psi hat TFD. And it has the property that the thermal expectation value of anything in the extended algebra is the same as its expectation value in this pure state. Because U is central in the extended algebra, the state psi hat is a sort of classical quantum state from the standpoint of this algebra. A classical state in U times a quantum state in psi in the rest of the algebra. Now, should we also add another central generator, U prime, which would be HL prime over N? In other words, should we do on the left the same thing we did on the right? The answer is no, because U minus U prime is just H hat over N, where remember H hat was HR minus HL. And H hat had a large N limit, so U minus U prime vanishes at N equals infinity. So in other words, to the algebras AL0 and AR0, we just add one central generator, U, which is shared by the two algebras. Because it's central, it's common to both algebras. So the extended right algebra is the old right algebra tensored with AU, the algebra of commutative functions of U. And the extended left algebra is the old left algebra tensored with the same AU. Since U is central, AU appears in both algebras. Now, the algebras AL and AR are of type 3 in the large N limit, as observed by Wertheiser and Liu. They're not factors because they have the central generator U. Factor is von Neumann algebra jargon for saying that the center is trivial. Trivial means that only complex scalars are in the center. Obviously, these algebras are not factors because U is in the center, and any function of U is in the center, so they have infinite dimensional centers. It's sort of non-generic for a non-commutative algebra to have a big center. What will happen is that one over n corrections deform the algebras, so U is no longer central, and therefore can no longer be common to the two algebras. The two algebras commute with each other. one is on the right, one's on the left through its space-like separation. So if U is not central, it can't be shared anymore. So the algebra will be deformed so that no operator is shared except a complex scalar, because the two algebras will be factors, and in the process, they will acquire a simpler structure. At n equals infinity, HR prime over n was well-defined and central, so we identified it with the central generator U in AR0 tensor AU. When we instead expand in 1 over n near n equals infinity, HR prime over n is no longer central. What it does is what I wrote before. HR prime generates time translations of the right algebra. And since it does, HR prime divided by n generates 1 over n times time translations. So it's central at n equals infinity, but of course it's not central at any finite n. To find the bulk dual of HR prime over n, we need to find a bulk operator that satisfies the same commutation relations. So what's a bulk operator that will reproduce this relation here? In a sense, that's the main idea of my talk. That question has a simple answer. There's an obvious answer, which is that H hat is a well-defined bulk operator that generates time translations on the right boundary. It also generates time translations in the opposite direction on the left boundary. But here, we're only interested in the right boundary because A is in the right algebra. So to find a bulk dual of HR prime over n, we need an operator that has the same commutation relations, and the obvious one is H hat over beta n. On the other hand, at n equals infinity, HR prime over n was dual to U, not H hat over n. So the simplest thing we can try is to have what we had at n equals infinity, which was U, and then we add a 1 over n correction to reproduce the 1 over n term in the commutation relation. So this is a formula that works in the sense that it has the right commutators with AR0 to this order in 1 over n. Well, of course, you should ask if corrections to the formula are possible. Without disturbing the commutators with AR, we could, of course, add something that commutes with AR. Well, what commutes with AR? Well, anything in the left algebra commutes with AR. So I could add a term B over n, where B is in the left algebra, and I could also possibly add corrections of order 1 over n squared in higher orders. You should worry about higher order corrections to the formula. But it turns out that these corrections are unnecessary because they can be removed by conjugation. So on the extended Hilbert space, which is the old Hilbert space tensored L2 of R, where U acts by multiplication, we haven't used it so far, but of course there is a conjugate operator to U, namely pi, which is minus ID by the U. And you'll see that conjugation by e to the IB times pi over n will remove the correction in the bulk formula for HR prime over n. And the same works order by order in 1 over n to all orders. So when you say what is the algebra dual to a given boundary algebra, of course, you have to let that answer is only well-defined up to a change of coordinates, which for non-commutative algebras means up to conjugation. So up to conjugation, there's no need for any corrections to this basic formula with the first two terms. That's true to all orders in 1 over n. We don't expect it to work perturbatively and non-perturbatively in 1 over n, because the series of conjugations we have to make may not converge if n is set to an integer. But as an asymptotic expansion in 1 over n to all orders, we can remove any corrections to the first two terms on the right-hand side here. We don't expect it to work non-perturbatively because when n is an integer, the algebra has to become of type 1, not type 2 infinity, which is what we're going to get. In sum, we can include 1 over n corrections by deforming the right algebra from the naive right algebra tensored with functions of U to the naive right algebra tensored with functions of U plus H hat over beta n. But I've replaced this tensor product symbol with this semi-direct product symbol because it's no longer true that this commutes with that. And the notation is meant to suggest that actually a guy in here commuted with a guy in here, well, will be in here. Well, I slightly oversimplified that, but roughly. Well, what about AL? If this is AR, what's AL? Imagine the first thought that comes to your mind is that whatever we did on the right, we should do on the left. But your second thought might be to see that that's wrong. AL is supposed to commute with AR. So the previous, we can't just imitate the previous formula and write gosh. This is supposed to be AL0 here. I can't erase it, but what isn't viable is that AL is A little L0 tensored AU. That's not viable because it doesn't commute with the deformed AR. And your first thought might be to make the same correction of both of them. Luckily here I don't have the misprint. So since if this is true for AR, then your thought might be to do the same thing for AL. But that's not viable because the two algebras are so defined don't commute with each other. This doesn't commute with AL0 because H hat generates time translations in the negative direction on the left. This doesn't commute with AR0 because H hat generates time translations in the positive direction on the right. So although I've argued that this formula for AR is true up to conjugation to all orders in 1 over n, we can't just imitate it in the obvious way for AL. However, once we identify AR, we can determine AL by saying it's the commutant of AR. In other words, the operators on the left of the horizon are simply going to be all the operators which commute with all the operators on the right of the horizon. Well, what commutes with AR? Well, we see right away that U commutes with AR because although there is a canonical conjugate to U, and we used it in arguing that AR can be conjugated into this form, the conjugate of U doesn't appear in the algebra, so U commutes with AR. So we can assume that U is in the left algebra. And although the naive left algebra doesn't commute with AR because it doesn't commute with this thing, we can conjugate it to something that does commute with AR. Because if I conjugate the naive left algebra using the conjugate of pi together with this operator H hat, then we find that this does commute with that. It commutes with U plus H hat over beta n. If you try it, you'll find it'll work. Whatever you get by commuting U with pi will compensate for the fact that H hat doesn't commute with this thing. So therefore, we get an answer for the left and right algebras. If this is AR, then this should be AL. It's generated by U together with a conjugated version of AL0. Now, you might be puzzled at the asymmetry between AR and AL because the problem had an obvious symmetry between left and right. However, that can be removed by conjugation. If you conjugate by the inverse of this operator, you'll remove these factors here and put in their inverses over here. You'll remove the H hat plus beta over n here, and you'll insert something like it over here. So conjugation by this operator will give you formulas that will look like this, but with the roles of right and left exchanged. The sign of H hat will change, but that's correct because H hat is odd under left-right exchange because it was defined as H right minus H left. It's also possible to give symmetric formulas, but they're more complicated. If you conjugate not by this operator, but by the same thing with half the exponent, you'll get formulas with manifest left-right symmetry, but they're a little bit more complicated and less convenient than writing something like this. So I'll prefer in the rest of the lecture to use these formulas. Now, from these formulas, you can see, at least heuristically, that the two algebras have been deformed so that their centers are trivial. For example, AR no longer contains U. U isn't in the center of AR because it's not contained in U. Oh, sorry, U is not contained in AR, so it's not in the center of AR. AR does contain U plus H hat over beta n, but that operator isn't central because it doesn't commute with AR0. It's true that AR does commute with U, but since U isn't, as I said, it's not in AR, so it's not in the center of AR, U is actually in AL. And that explains why it commutes with AR, because AL commutes with AR. So AR commutes with roughly as much as it commuted with before, but it doesn't commute with anything that's in AR. You see, AR used to commute with AL, and now it commutes with the deformed AL. The deformed AL is just as big as the old AL was. So each algebra is as big as it was before and has as big a commutant as it had before. The commutant of an algebra being everything it commutes with. But previously, the algebra and its commutant had a non-trivial intersection, the center. Everything has now been a little bit rotated or deformed so that the intersection of the algebra with its commutant is trivial, which of course is a more generic situation. So the fact that the previous situation was non-generic is the reason that a simple 1/n perturbative correction could make a big difference. And now that we're in a more generic situation, I do not expect perturbative corrections beyond this to make a big difference in the same way. So what I said here was heuristic. A complete proof that the centers are trivial depends on something I'll explain later. So the duality says that big AR, well, A sub big R is the same as A sub little r, and A sub big L is the same as A sub little l. So with 1/n corrections included, the algebras of operators to the left or right of the horizon have trivial center. The preceding formulas imply the following important fact. To all orders in 1/n, the algebras have an outer automorphism that's not present in the exact theory. That's the outer automorphism generated by the group pi. Well, the group pi that shifts U by a constant is an outer automorphism. It's an automorphism of AR because since a constant anyway is in the algebra AR, see, the constant C anyway is in the original algebra because a C number is in all our algebras. So it doesn't matter whether we join to the algebra U plus H hat over beta n or the same thing plus C. Since C is already in the algebra, adjoining this or this to the algebra gives the same result. So therefore, e to the IC pi is an outer automorphism of this algebra AR, and the same thing works for AL. It'll turn out that this outer automorphism group shifts the entropy by an additive constant, and that explains why using only the information contained in the algebra in an expansion around n equals infinity, we can only define entropies up to an additive constant. Let's compare these formulas to the discussion by Jafris, Lefkowitz, Montesana, and Su. Their formulas were written in terms of modular Hamiltonians. So that of the right boundary is minus the log of rho sub r, where rho sub r is the density matrix of the right boundary. So the right modular Hamiltonian is this thing, where you can think of here, log z as a C number, its thermal excitation value. So the right modular Hamiltonian is HR times a constant plus a C number. Similarly for the left modular Hamiltonian. And then the JLMS formulas can be written this way in terms of little hr and little hl, and A over 4G, where A is the area of the horizon. Another way to write the formulas is in terms of the thermal entropy, which is the thermal average of A over 4G. And then the formulas look like this. So the relation between the formulas I've derived and those of JLMS is just what I've written here on the bottom. So my U up to a shift and also a multiplicative constant is the same as the operator on the right-hand side of the of this version of the JLMS formula. It's believed that of the three operators, little hl, little hr, and a over 4g, only the two linear combinations that appear on the right-hand side of the JLMS formula are well defined. Well, I explained to you why little h, one of these should be L instead of R. I've explained to you why little hl and little hr aren't well defined. But the JLMS formula, since the operators on the left are well defined, JLMS formulas show that these combinations must be well defined. So HL and HR are not well defined, but these combinations, except that that should be an L here, are well defined. Maybe I'll just even correct it. So anyway, it's believed only these two linear combinations are well defined. That's related to the observation of Susskind and Uglin that the generalized entropy is better defined than either term is separately. It's a somewhat similar observation, although I don't think they're trivially connected. If you believed all three operators are well defined, you'd probably decide that HR is in the right algebra because it's given by an integral outside the horizon. HL is in the left algebra since it's given by an integral to the left of the horizon. And then since HL prime and HR prime are in the left and right algebras, these formulas would tell you that A is in both algebras and therefore is central. So as we've learned, that's actually true at n equals infinity, but not when the 1 over n corrections are included. What we've run into is a construction that's actually important in the mathematical theory of von Neumann algebras. This thing that I've called, well, AR0, I use the symbol, sorry. When I wrote it before, I didn't use this tensor product symbol, but this other formula that I'm having trouble writing at the moment. That one for the semi-direct product. Anyway, this thing is called the cross product of AR0 by its modular automorphism group. So why is it important mathematically? Well, a type 3 algebra such as AR0 is difficult to study. Takasaki and Kahn discovered half a century ago that the cross product of a type 3 algebra by its modular automorphism group is an algebra of type 2, easier to study. Moreover, it turns out that what one learns about the type 2 algebra can be used to understand the more difficult type 3 algebra. So that's what they were doing. In the rest of the talk, I'll mostly explain some of this. Suppose an algebra A acts on a Hilbert space H, and let T be a self-adjoint operator on the Hilbert space that generates a one-parameter group of automorphisms, which simply means that if you conjugate by e to the its, where s is a real number, you get an element of the algebra. So it conjugates the algebra to itself. Let L2 of R be the Hilbert space of square integrable functions of a variable x. The cross product algebra, sometimes denoted this way, A times R sub t, is the algebra acting on H hat, which is H tensored L2 of R. It's generated by A tensor 1 and by e to the ist tensor e to the isx, where s is a real number. More informally, it's defined by adjoining t plus x to the algebra A. In other words, the cross product is exactly what we've run into, but with, well, x was called u in my previous discussion, and t was little h hat times a constant. The cross product is not interesting if the automorphism is inner. That means if t is in the original algebra. For then adjoining t plus x to the algebra is the same as adjoining x, since t is already there. And therefore, A cross product with R sub t is just a trivial tensor product where you've just adjoined a trivial center to the algebra, the center generated by x. So in other words, in the case of an inner automorphism, all the cross product does is to adjoin to our algebra a central element x. That won't really teach us anything new. We're really only interested in the cross product in the case of an outer automorphism. The case of interest to us is the cross product by the modular automorphism group. For that, let psi in Hilbert space be a vector that in the jargon is cyclic separating for A. If you don't know the terminology, let me just say that the thermofield double state satisfies that definition if the algebra is A sub R. So in our application, psi will be the thermofield double state. Let delta be the modular operator of psi for the algebra A, and set delta equals e to the minus h hat. So in our application, the h hat that appears here is actually what I've been calling h hat, hr minus hl, the operator that generates time translations forward or back on the two sides. The main theorem of Tomita-Takasaki theory says that h hat generates an automorphism of A. If A is of type 1, this is an inner automorphism, which can be described by density matrices. But for type 3, which is the case we're interested in, it's an outer automorphism. A look back at our description of the algebra outside a black hole shows that up to trivial rescalings, it's precisely the cross product by the modular automorphism group. Because of the apparent dependence on psi, I'll include psi in the notation and write AR as the cross product of the algebra ignoring the center with the modular automorphism group of psi, where for us psi was the thermofield double state. However, an extremely important point in the mathematical theory of von Neumann algebras is that the cross product by the modular automorphism group does not depend on psi. That would not be true if we naively adjoin minus log delta to the algebra. It is true if we extend the Hilbert space and adjoin h hat plus x. So in other words, the operation that gravity told us to do is the one that half a century ago the mathematicians found gave a simpler answer than the more naive procedure without x. We might call the fact that A semi-direct product R psi doesn't depend on psi state independence, and I hope it's a step toward what we usually call background independence in physics. But I won't really make a technical claim today in that direction. The proof of state independence is made using what's called the Kahn cocycle, which has been used in several recent papers on gravity. Well, I've written the definition of the Kahn cocycle, but I won't explain much about it. Well, Kahn proved it's valued in the algebra. And then there's a similar Kahn cocycle for the commutant of A. And then there's an explicit formula that shows that the cross product algebra doesn't depend on the state up to conjugacy. And that formula is explained in my paper, but it's a little technical, so I won't explain it in the lecture. What was useful about this to Kahn is that in case A is of type 3, the cross product is simpler than A being of type 2. That's the result I advertised at the beginning. 1 over n corrections turned the algebra from type 3 to type 2. And then Kahn used that to study the original type 3 algebra. But to understand why the algebra is of type 2, we could proceed as follows. We had before a simple state, the extended thermofield double state. We took the ordinary thermofield double state and extended it by g of x to the 1/2. And that was a cyclic separating state for the bigger algebra because it is the thermofield double. So now we can apply modular theory and compute the modular operator delta hat for psi hat in terms of the modular operator for psi. And you can get an explicit formula, which I've written here. Again, it's explained in my paper. I won't explain it in detail now. What's interesting about the formula is that it can be factored as an element of the algebra times an element of the commutant. So in ordinary quantum mechanics, you always have such a factorization. If you have a bipartite Hilbert space, bipartite system XY with a tensor product Hilbert space, A is the algebra on HX, the commutant is the algebra on HY. For any state psi, we'd have density matrices rho x and rho y, and the modular operator is given by an elementary formula involving density matrices. So you see two things are true here. The Hilbert space is a tensor product, and the modular operator is a product of an operator from one algebra times an operator from the other algebra. For type 3, and thus for the algebra of the local region in quantum field theory, neither of those things happens. Type 2 is the intermediate case. The Hilbert space does not factor, but the modular operator does. So in our case, the modular operator has a simple factorization where as k times k tilde, where k tilde is only a function of x. So it's in the commutant. And k is only a function of h hat plus x because of something I haven't written right here. You have to remember that delta is e to the minus h hat. From which you see that k is only a function of h hat plus x. And since h hat plus x is in the cross product algebra, oh, maybe I have explained it. Sorry. This is what I said. So what I just said is explained here. So k has been written this way. It's a function only of h hat plus x, which is in the cross product of the original algebra. So therefore, the formula that the modular operator is k tilde shows a factorization. Once you have a factorization of the modular operator, you can define a trace. The trace is defined by this formula. It's the excitation value in the state psi of a hat times k inverse. You can guess that formula. Well, a fairly straightforward calculation shows it is a trace, meaning that the trace of a hat b hat is the trace of b hat a hat, assuming the trace is defined by this formula. So again, that computation, a couple of versions of it actually, are contained in my paper. I won't explain it for you right now. Important thing, though, is that the trace isn't completely canonical because the factorization could have been made with k and k tilde both rescaled by a positive real number. If we rescale k by e to the minus c, because of the k inverse in the definition of the trace, that'll rescale the trace by e to the c. So we do have a trace, but we don't know how to normalize it. We only have it normalized up to a multiplicative constant. It's possible to write a more concrete formula for the trace. If you have an element of the algebra that's of this form, then its trace can be written this way. Again, all those calculations are in the paper if you want to see them. This formula is also useful for helping us see for what class of elements of A times R psi this trace is convergent. But something else it's useful for is that it shows us that if we shift x by a constant, the trace will be, e to the x will be multiplied by a constant, and therefore the trace is rescaled. And remember, shifting x by a constant was an outer automorphism of the cross product algebra. And therefore it's impossible using only the structure of the algebra to determine a natural normalization for the trace. You'll see why that is interesting in a second. Before that, though, I want to just remark that it's known that the cross product algebra A crossed with its modular automorphism group is a factor, meaning trivial center, if and only if A is of type 3-1, which is the case we're interested in. So precisely in the case that arises for the black hole, the cross product algebra has trivial center, and the left and right algebras have no central operators in common. And moreover, it's also a standard fact that when A is of type 3-1, A cross semi-direct R psi is of type 2 infinity. So as I've told you, AR and AL in the context of 1 over n expansion are factors of type 2 infinity, and in particular, they have trivial center. Whenever a von Neumann algebra has a trivial center, a trace, if it exists, is unique up to a scalar multiple. So the ambiguity we identified is the only ambiguity. Where did we identify it? Well, I guess, who knows? Somewhere we identified it, back here. That's the only ambiguity because the algebra has trivial center. Well, I've mentioned the reason already, but here I have a slide to explain the fundamental reason we can't eliminate this indeterminacy of the trace. The cross-product algebra has this group of outer order morphisms that shifts x by a constant. Because of the e to the x in some of the formulas, this outer order morphism multiplies the trace by e to the c. So therefore, using only information in the structure of the algebra, we can never give a natural normalization of the trace. There's an outer order morphism that would rescale the trace. Once we have a trace, we can define a notion of density matrix. An element rho in the cross-product algebra is the density matrix of the state chi if for any operator, the expectation value of a hat in the state chi is the trace of a hat times rho. Same definition as in ordinary quantum mechanics. Such a rho will exist because the trace is non-degenerate and the left-hand side is linear in a hat. So there will be some linear operator that will make the right-hand side equal to the left-hand side. Assuming that the state chi is normalized to 1, as usual, the trace of rho will be 1, like a density matrix in ordinary quantum mechanics. If we rescale the trace by e to the c, we'll have to rescale the density matrix by e to the minus c. Once we have a trace, we can define a version of the von Neumann entropy. Usual definition. However, only entropy differences are really meaningful, because if we rescale the trace by e to the c and the density matrix by e to the minus c, you'll see that the entropy is shifted by the additive constant c, the same for all states. That's analogous to classical mechanics, where, as I mentioned before, entropy differences are defined by formulas such as the first law of thermodynamics, dE is TdS minus PdV. But there's no natural way to fix an overall constant in S, an overall additive constant. We can similarly define Rényi entropies by the usual formula, and now they have an indeterminacy that depends on the same constant C. As an example, we can calculate the entropy of the classical quantum state, side center g of x to the 1/2, where psi is the thermofield double state. In this case, you find that the density matrix is just K. And the entropy is given by this integral. I want to stress again that these entropies are defined only up to an arbitrary additive constant. So it's really only entropy differences that we're talking about here. So thank you very much. Okay, well, I have a slide summarizing. In short, we found that a simple correction of order 1/n improves the algebra of operators outside the horizon, converting it from type 3 to type 2, and in some ways reducing the gap with ordinary quantum mechanics. Thank you for your attention.
Okay, thank you very much for your great talk. Question, please. Let me see. Igor, we have a question from Igor Valovich. Igor, please ask your question.
Thank you very much for the nice talk. I have a few questions. First, is it true that your density matrix, that your trace will be equivalent to the ordinary Gibbs distribution, like in Hawking case?
Well, all I'm doing is expanding the standard story in powers of 1/n. So why do I not? Okay. The trouble with your question is that it's difficult to explain in what sense the standard Gibbs distribution has a large n limit.
I mean, Hawking has in a well-known paper.
Let me give you a better answer. So see, the usual density matrix does not have a large n limit. Let me, maybe instead of talking about large n, let's talk about quantum statistical mechanics. There's a more elementary problem. An elementary fact, but something we don't usually think about, is that the Hamiltonian in Hilbert space in quantum statistical mechanics in volume V have no large V limit.
Of course, I know this. I mean, functional.
Perhaps not every state. What's that?
I mean, the notion of state, which is valid in large volume V.
What does have, well, let me explain to everyone.
Which comes from Gibbs distribution, according to Hawking.
The thermophile double Hilbert space do have a large N limit. So that's sort of why the thermophile double is useful in rigorous statistical mechanics. It has a large volume limit, unlike the one-sided Hilbert space and Hamiltonian. The Hamiltonian can't have a large N limit because it's, well, first of all, its average value diverges for large volume, but even if you subtract the average value, its fluctuations also diverge. So the Hamiltonian does not have a large volume limit. Likewise, the Hilbert space doesn't. However, the thermophile double does have a large volume limit. Now, what's true for large volume is also true for large N. And remember, large N corresponds, let me make an analogy. What in the usual case is V going to infinity is similar to N going to infinity. So when N goes to infinity, the conventional Hilbert space and Hamiltonian don't have a large N limit. That's the problem with your question. So the standard rho does not have a large N limit. The Hilbert space at X1 also does not have a large N limit. What I've done is to explain that the algebra of operators has, well, first of all, what Liu and Leutheiser explained is that although the Hilbert space and Hamiltonian don't have a large N limit, the algebra of operators does have a large N limit. And then I've explained that expanding near the large N limit, we can reconstruct some of the properties that would have come from ordinary quantum mechanics, but not all. Of course, if we could reconstruct all of the properties, we would have solved the black hole information problem. We have not done that. We've only recovered some of the properties of ordinary quantum mechanics. I don't know if I've answered your question or not. If not, please ask a follow-up.
Yeah, thank you. I will think about this. I have another technical question. You consider an algebra of gauge invariant operators.
Yes.
Right? But gauge invariance requires indefinite metric, like Gupta-Bleuler.
Like what?
Like Gupta-Bleuler formalism. I mean, gauge invariance requires indefinite metric.
Well, if a gauge theory makes any sense, if a gauge theory makes any sense, we've learned how to define a gauge invariant Hilbert space. Gupta-Bleuler is one formalism. But if gauge theory makes sense, we've somehow learned to define it, a physical Hilbert space. And the operators we're discussing are the operators on the physical Hilbert space. There are different formalisms we could have used to define a physical Hilbert space, but somehow we decided that the theory exists. So I didn't try to prove that gauge theory exists in this lecture, but somehow the fact that it exists was the input, part of the input.
Okay, thank you. And last question. How you prove that your algebra is of type 2 von Neumann?
Well, it's of type 3. Without including the center, it was of type 3. Because, well, Leutheiser and Liu give a couple proofs. The quickest proof is just that it's dual to the bulk operators outside the horizon. And the bulk operators outside the horizon are the operators in part of space. And in general, in quantum field theory, that's of type 3. Then when I have the center, why is it of type 2? It's of type 2 because it's the cross product of a type 3 algebra by its modular automorphism group. And by, according to Takasaki and Kahn, that's of type 2. So, okay, it's a classic mathematical result, but in a sense, I sketched a proof. Except that if you want to see the details, you have to look at the paper. But what I told you was that you could compute the modular operator of this extended thermophile double state, and it factorized. Sorry to scroll through all these pages. I don't remember where it is, what I'm looking for. Okay. Well, it depends on what you know about von Neumann algebras to begin with. But first of all, this formula I wrote for you, but I didn't prove it. It's proved in my paper. It's proved in my paper, but I wasn't the first. All this stuff goes back to Kahn and Takasato. Maybe it's better to say not that I proved it in my paper, but I explained the proof in my paper. All proofs in my paper are just classical mathematical results that Roberto Longo helped me understand and that I tried to explain for physicists in an understandable way, myself being one of the physicists that was trying to understand them. Then, after finding this formula, it factors as k tilde. Depending on what you already know about von Neumann algebras, that factorization proves that this has to be of type 1 or type 2. But then the fact that there's an outer automorphism that rescales the trace shows that it has to be of type 2 infinity. However, in the last two sentences, I quoted some results about von Neumann algebras. I'm not proving everything from first principles. I am invoking standard facts about von Neumann algebras and telling you various ways one can do that. Any more questions?
Okay, next question is come from Atish Dabholkar. Please, Atish, ask your questions.
Hi, can you made the statement that the fact that the von Neumann algebra is type 3 is a manifestation of information problem. Can you elaborate on this comment?
Well, in ordinary quantum mechanics, okay, if it were of type 1, it would have an irreducible representation in a Hilbert space, and that would be the Hilbert space of black hole microstates. So black hole microstates are the pure states of the algebra of operators. But a type 2 or type 3 algebra doesn't have pure states. So there aren't any black hole microstates in the large N limit. And there's a certain sense in which there can't be. I think it's an elementary but important fact that H has no large N limit. And likewise, the Hamiltonian. So this is for states that are above the threshold for black holes. If you take the large N limit, keeping the energy fixed, the Hamiltonian and Hilbert space have a large N limit. You don't see black hole states in that limit. You see integrability, the opposite of black holes. Black holes are chaotic as far as possible from integrability. If you want to see chaos in black holes, you take n to infinity with the energy of order n squared. And also E over n squared has to be big enough. I claim in that limit that the Hilbert space and Hamiltonian have no large N limit. So there isn't a large N limit of the black hole microstates. And a reflection of that is that the algebra at n equals infinity is type 3, and a type 3 algebra has no pure states, which would have been the large N limit of the black hole microstates. So we have to get away from, now remember, n equals infinity corresponds to g equals 0. So another statement is that g equals 0, you can't make sense of black hole microstates. We need to get away from n equals infinity or g equals 0. In today's lecture, we've only gotten away from n equals infinity perturbatively. And perturbatively in 1 over n, type 3 went to type 2. And it was a little bit better in that the modular operator factorized, and we could define a trace and an entropy, or at least we could define an entropy difference. We still do not have pure states. So in perturbation theory in 1 over n, there is no notion of a black hole microstate. Black hole microstates, I believe, only exist for specific values of n. I don't think they can be expanded in powers of 1 over n. Why do I think so? Well, the same thing is true in statistical mechanics. The microstates don't have a large volume limit, and they can't be expanded in powers of 1 over the volume either.
Okay.
But there's no information problem in statistical mechanics, right?
No,
what you're suggesting is...
Well, there isn't, because we're not... But if we only had the large volume limit of statistical mechanics and we were trying to figure out what happened in finite volume, there would be. So in the infinite volume limit of statistical mechanics, there are no microstates, and that doesn't bother us. I might tell you, most physicists don't say that there are no microstates in the infinite volume limit. What do most textbooks tell you to do? They tell you to work in finite volume where there are microstates. Then, I need space to write on. In finite volume, the density matrix is well defined. It's given by a standard formula. One of the questions was how what I'm saying compares to the standard formula. This is well-defined formula in finite volume. Then you use it to calculate the thermodynamic functions. You do that by summing over microstates to compute the entropy or whatever. Then the textbooks tell you that the thermodynamic functions have a large volume limit. They don't tell you that the microstates didn't have a large volume limit, and usually you don't think about that. However, the microstates do not have a large volume limit. So the reason we say there's no information problem in statistical mechanics, well, the information problem would be to describe the microstates for finite volume, but we knew how to do that. Then we went to large volume where there weren't microstates anymore, and we didn't usually talk about that. But people in rigorous statistical mechanics introduced the Thermofield double because it is a well-defined Hilbert space in which to discuss the large volume limit. Anyway, for black holes, we have the large M limit, which is the analog of the large volume limit. And the information problem is that we don't know how to say what's happening at finite M.
Okay, the next question is from Ruka Smalden. Ruka, please ask your question.
Can you hear me?
Okay.
Yeah, okay. Just curiosity. When you deformed the left and right algebras, it reminded me a bit, some papers where the thermofield dynamics was studied in the framework of quantum groups, in particular of quantum Heisenberg group, or the Q Heisenberg group. So I clearly, because in that case, the B-algebra structure of quantum groups is very suitable for the study of thermofield dynamics and establishing of degrees of freedom. And so I was wondering if your deformation can be put in connection with Q deformation.
I can't answer that question. I'm really not familiar with what you're saying about Q deformations being useful to study thermodynamics.
Yeah, it is a paper, or more than one paper, 1996.
Could you send me by email? Could you send me by email the most useful reference to look at?
Yeah, sure. And just a curiosity from your last question. So you are claiming, or maybe not, that information paradox could be related to the inequivalent representations of canonical commutation relation in quantum field theory?
I'm not exactly claiming that, but I'm claiming that for large, at n equals infinity, we're running into things that are easier to understand at large volume. By the way, I gave a lecture and wrote up a lecture on quantum field theory in curved spacetime and also the large volume limit of statistical mechanics. So some of these questions about the non-existence of the large volume limit and why the Thermofield double is useful are discussed in that lecture and the written version. You could look at it.
Sure, because it reminded me, clearly, this kind of arguments are usually studied when you discuss inequivalent representation and violation of Sturm-von-Neumann theorem. So yeah. I was wondering, you were connecting the entropy.
I'm not really relating the black hole information problem to that. I'm relating it more to it is true that at n equals infinity, the nature of the algebra changes. Mm-hmm. And there aren't pure states anymore. That's the essence of the black hole information problem, I would say.
Mm-hmm. I see. Thank you very much. I will send you the papers.
Okay. The next question from Robert Brandenberger. Robert, please ask your question.
Let me just, Luca, please send me the most useful paper, not all of them.
So,
okay. Go ahead.
Ed, a crucial point was that you can only define a trace if the algebra is type 2 and not type 3. Can you repeat the argument for that? Because I didn't understand it.
Well, I did define the trace for type 2. And I used the fact that the modular, I defined it. Again, it's going to depend on what you already know. The definition of the trace literally was this. Where the definition of K was that it appears in this factorization.
So the key point is that for type 3, you can't define a K.
Yes. So actually, remember, for type 3, delta was e to the minus h hat. And you could, the factorization is wrong because it's not, well, okay.
Thanks.
Okay. So why, but let me say more informally that why there's no trace for type 3. I mean, if you take the Hilbert space of a quantum field theory and you try to take a local operator that only acts on the right, you've never run into anybody telling you what is the trace of an operator that acts on only the right. Any attempt to define such a trace is hopeless because with you'd be summing over infinitely many things that can happen on the left. So any trace would be infinite, and there's no way to regularize it. Maybe nobody ever told you they couldn't define such a trace, but nobody ever did want to define one for you. And if you think about trying to define it, you'll quickly get very discouraged. Because if you take the operator O that acts only on the right and try to take its trace in the big Hilbert space of all states in the whole universe, since O only acts on the right, it doesn't know what's happening on the left. And there are infinitely many possibilities that could happen on the left that O can't distinguish. So the trace will trivially be infinite. Is that clear?
Yes, yeah.
Good. So therefore, it should be surprising that we were able to define a trace. I was surprised. When I started, I had only very faint hopes of getting a type 2 algebra. But I didn't know about well, to be honest, I knew that I'd been exposed to the work, to the words about Kahn and Takasaki relating type 3 to type 2. I knew that the black hole information problem was a problem because the algebra was a type 3. And since mathematicians had somehow related type 3 to type 2, I thought maybe we could do it too as physicists. I started literally not knowing anything more than I just told you in that last 2 sentences about what Kahn and Takasaki had actually done. It just turned out that their construction made sense in physics when you take into account the fact that the algebra looked at by Liu and Leutheiser had a center. Okay, another question?
Okay, the next question is a question from Yap Bauri. Sorry, maybe I pronounced your name not correctly. Please ask your question.
Hello, can you hear me?
Yes.
Hello. This is also maybe related to the trace. Is there an easy way to see why we have type 2 infinity rather than type 2 1, say?
Well, we had an outer automorphism that rescales the trace. For type 2 1, there's no such outer automorphism. Did you understand what I said? We have the outer automorphism that shifts x by a constant. And it rescales the trace. Type 2 1, see, for type 2 1, you can normalize the trace such that the trace of the identity is 1.
Yes.
Any outer automorphism.
And such rescaling would.
Yeah. Well, let me say it for everybody else, though. Any automorphism of the algebra has to map the identity to itself. So it's impossible, given this fact, for an outer automorphism of the algebra to rescale the trace. So what shows that the algebra is type 2 infinity rather than type 2 1 is that it has an outer automorphism that rescales the trace. And incidentally, that was used by Takasaki, who took the cross products with the outer automorphism group and got back the original algebra. Why that's useful in physics, I can't tell you. Not yet. Any other questions? I see one by Bave Slava or something.
Okay, there is a question from Bayat Tayegi, please.
Yeah, right. Could you briefly comment on the restrictions to further convert it to type 1 algebra?
need a better idea. So one expects that non-perturbatively, sorry, when n is an integer, you expect to get a type 1 algebra. But in an asymptotic expansion, trying to understand what happens when n is an integer is like trying to do non-perturbative physics. I only did perturbative physics in today's lecture, perturbative in 1 over n, and I only analyzed a particular term. So I don't really know how much harder it is, but naively to do non-perturbative physics might be much harder than what I did. Or might need a much deeper or better or more far-reaching idea, who knows? I can't tell you how to do a non-perturbative description.
I was only wondering if there's some, there's something that we keep following up the order of perturbation or something.
Well, I haven't even done perturbation theory in higher orders. I told you heuristically why I don't expect perturbation theory in higher orders to change the picture at this very general level of what type of algebra it is. I didn't prove that, but that's what I expect. Non-perturbatively, we expect the nature of the algebra to change, but I don't know how to demonstrate that directly.
Right, okay, thank you.
Sure.
More questions, please? Maybe in this case, I will ask a questions. Still, there is one more questions from, no, this is not a questions. Okay, well, my question is the foreign one. What happens if we consider charged black hole, the case when there are some extra horizons or something like that? What could be the situation?
When you say extra horizon, you mean the inner horizon?
No, for example, if you consider the charged black hole,
yes,
Reisner-Nordstrom ADS black hole, what happens?
As far as I know, everything I said applies to that case. The center, as I said, corresponds to the conserved charges. Mm-hmm. So I didn't discuss the other conserved charges, but there can be some. So there's angular momentum so you could have asked me about the Keras black hole. And there can be gauge charges, and we could discuss a charged black hole. Mm-hmm. As far as I know, the other charges don't change the nature of the algebra. You get a bigger cross product. It's discussed at the end of my paper. You get the cross product not just with the modular automorphism group, but the whole automorphism group, including the automorphisms generated by the other charges. Mm-hmm. But okay. I always could have missed something, but as far as I know, the cross product by the other automorphisms doesn't lead to any interesting surprises. If you're interested, you could look at what I said in the last few pages and form your own opinion.
Could you write down the references again, please?
There's only one well, there's two references. There are two papers by Liu and Leutheiser. I had the archive numbers at the beginning, but I don't remember them. And there's one paper by me. Mm-hmm. These papers are in the archive in the last couple months.
Okay.
There's one paper by me, but there's one before that isn't really necessary to understand this lecture, but it might help you understand better some statements, like the fact that the Hamiltonian and Hilbert space have no large n limit. That's the write-up of the lecture on curved spacetime and the large n limit. Oh, sorry, the large volume limit.
Okay, thank you. Thank you very much. More questions, please? I still have, I see questions from Maitra. Please ask your question.
Yeah, I was wondering if we consider exactly extremal black holes, which do not have the double-sided description, what aspects of the construction would need to be changed?
Well, that's a great question. Of course, a two-sided black hole, sorry, an extremal black hole, which you're asking about, is very delicate because if you perturb it slightly, it stops being extremal.
Right.
But let's try to take your question literally and start with the strictly extremal one. So first we should repeat the analysis of Liu and Leutheisser. They can still define a large n limit, but we should ask what kind of algebra it is that we get. The answer is less obvious though. I think we should start by asking the following question. Can we define a Hilbert space of small fluctuations around the extremal black hole just by bulk quantization?
I see.
If the answer to that is yes, then the large n algebra is going to be just of type 1.
I see.
Okay, more questions, please.
Thank you very much.
I wanted to say more about that though.
Oh, sure.
I'm not sure if the answer is, what is the answer? Well, okay, here's a question we ought to ask, independent of anything I said in my lecture. Is the Hilbert space just a tensor product of extremal black hole states tensored with the Hilbert space of outside stuff, or is it more subtle than that? I feel it should be more subtle. But if that's true, you'd think that if you tried to define the Hilbert space of outside stuff, you'd have trouble. So when I asked if you can define the Hilbert space of small fluctuations in bulk around the extremal black hole, that was meant as a real question. I'm not sure about the answer. I can't immediately see technically why you can't. On the other hand, if you can, it seems to me you'd be getting the wrong answer physically, because I think the correct answer shouldn't be a simple tensor product of extremal states with an outside Hilbert space. However, I'm not sure it shouldn't be either. I think the only quick answer to your question is I don't know. It's worth thinking about more. Perhaps some things I've said would be useful to you in trying to think about it more.
Sure. Thank you very much.
Sure.
More questions? I see one more question. One question from Arm Then please ask your question. Very difficult pronunciation. Please.
I think you're muted.
Sorry.
You can't
unmute yourself.
Okay, can you hear me now? Okay.
Yes.
So in string theory, there was also this old paper by Susskind and Uglum in 1994, where the sphere partition function sort of has this open string factorization near the Rindler space.
Yes.
As a trace. So can we phrase that in string theory in that sort of type 3, type 2 infinity? So in the closed string channel, that would be type 3. We cannot only find an open string representation in type 2. Is that because it seems to?
Well, I think it's a good question, to be honest. I'm not going to be able to answer it. The Susskind-Uglum idea is very interesting. Nobody's been able to make it quantitative. And making it quantitative would be very important, I think. Oh, yeah. Well, maybe I'm not adequately informed about what, okay. It hasn't been, I'm a little worried it's a statement about me. It hasn't been made quantitative in a way I understood. Okay. Okay. I don't think the Susskind-Uglum picture is understood very well, and I think it would be important to understand it better. And as for whether what you say would help in understanding it better, I really don't know. I don't know what would. I'd encourage, though, any efforts to understand the Susskind-Uglum picture better.
Okay, well, we're working on that actively with Aaron Wall. So.
Aaron Wall told me about it. Yes.
Yeah.
Okay,
so,
good. Good luck with that.
Thank you, Richard. Also, is this whole idea of the large n limit, is it related to also in string theory, what you discussed at some point in your 1988 paper with Attic, sort of as the large or the semi-classical limit in string theory? Sort of, can we able, because there's also a tension between the large n limit basically and, well, the gene's instability sort of thing. Is this related to this?
By n there you mean volume?
Yes. Okay.
Well, definitely that. I don't understand the question precisely.
So basically in that paper, there was a discussion of the Hagedorn transition in string theory as a first order or a second order phase transition. And it was pointed out that because of some sort of the sphere partition function has this large latent heat, and there was this tension between also finding the large N limit in string theory and the fact that there's gravity, and both there's a tension there. And so in a sense, this seems like also a factorization problem that is related to the earlier question, the fact that you cannot find a tensor product representation because of the sort of finding the large N limit, the non-existence of a large N limit, basically.
Mm-hmm.
In string theory, of course, again. So that was in string theory in that paper. So I'm trying to recast my understandings of that problem, whether it's a Susskind-Uglum problem, or whether it's this sort of Hagedorn transition problem or the big QT transition on the world sheet in that sense. In that new language of von Neumann algebras, basically.
I see. Well, I feel that I'm having trouble with the question about the thermal ensemble, but I feel it's really unstable in gravity in flat space. So I don't think we'll be able to fix that. On the other hand, the Susskind-Uglum story sounded very promising, and there might be a way to make that quantitative. I think that's about all I can say now.
Thank you. I appreciate that. Thank you so much.
Sure. I'm looking forward to whatever you can say about Susskind and Uglum for sure.
Yeah.
I told him there, and he told me.
We'll have a paper out very soon. Yeah.
More questions, please. I don't see any. Okay. If there is no more questions, let's thanks Ed once again for his great talk. Thank you very much.
Well, thank you for the invitation.
Thank you very much. Thank you very much.
Thank you very much.
And could you please also send transparencies to us, maybe to Alexei Koshelov, okay?
Yeah, no problem. I'll send them as soon as we get them.
Thank you. Thank you. Thank you very much. In fact, it was a great event for our seminar to have your talk, yes.
I'm glad I declined a couple of previous invitations telling you I didn't have anything interesting to say. It was much more satisfying to give a talk when I had something a little more interesting. Anyway, thanks so much for the invitation.
Yeah, thank you very much.
Thank you very much.